Hi guys, and welcome back to my channel. In this video we'll talk about atomic orbitals. And you probably heard about atomic orbitals in AP chemistry or a general chemistry class. You probably heard that of the s orbitals, the p orbitals, the d orbitals, and the f orbitals, and those like groups in the periodic table. But in this video we're going to delve a little deeper into what those orbitals actually mean, what they actually represent, and how we can represent the electrons in those orbitals using the idea of wave functions, which we've sort of touched on in previous videos. Now I just want to talk about what atomic orbitals actually are. So atomic orbitals are wave functions of electrons in atoms, right? We've talked about wave functions of electrons when we're looking at an electron in a particle in a box. We actually calculated that using the Schrödinger equation in a previous video. Now with atomic orbitals, we're looking at electrons in atoms and specifically their wave functions. And we calculate these atomic orbitals using the Schrödinger equation, but we don't actually have to know that deep into it for our purposes. The wave functions when we're looking at atoms, right? We're looking at 3D, right? Because atoms are spherical. Generally, we can regard them as sort of like a sphere. It's a three-dimensional object, right? Rather than when we talked about particle in a box. When we talked about particle in a box, we were looking at a one-dimensional system, a sort of linear box, right? So we were looking at a one-dimensional system with particle in a box, but now we have an electron that has probability density in all three dimensions, right? So what does this mean, sort of? We can think about the number of quantum numbers we're going to need to represent our electron or our orbital, right? So when we looked at a particle in a box, we needed one quantum number, which was our n quantum number, to describe an orbital in the particle in a box system. When we look at a 3D system, we can sort of think ahead, and we're probably going to need 3 quantum numbers. So this is just thinking ahead, and when I actually get to explaining quantum numbers, I'll show what the 3 quantum numbers are. But we can see that we'll need 3 quantum numbers because there's 3 dimensions. And to represent our atomic orbitals, to represent our wave functions, we use spherical coordinates. So instead of using an XYZ system or Cartesian coordinate system, we're using this new form of coordinates, which is called spherical coordinates, and it's really not that complicated. Basically, we have a radius, a latitude, and a longitude. So instead of using X, Y, and Z, we're using like a radius, a latitude, and a longitude to specify a point in space. So now we can look at what our psi looks like. So what does our wave function look like for an atomic orbital? We have a wave function, and again, we're taking in r, theta, and phi. And theta and phi are our latitudes and longitudes. R is our radius. So it turns out that atomic orbital wave functions can be decomposed to an angular part, which we call y, theta, and phi, and our radial part, which is r of r. So basically, we have a radial wave function, which only depends on our radius, and we have an angular wave function, which only depends on our angles, and our actual wave function is just the product of these two. So we can sort of decompose our actual wave function into two simpler functions. So what exactly does r of r mean? Let's sort of discuss these two parts. What is the radial wave function? Basically, this is saying, as I move away from the nucleus, as my radius increases, how does the wave function change, right? It's basically simple like that, because it's only taking in our radius. Now, what is our y, theta, phi telling us? This is the angular wave function. So this is basically saying, as I move along a spherical shell of a fixed radius, so if I take a spherical shell, so this is my spherical shell, and I'm only looking at the outside, this radius, my y function tells me how does the wave function change along my spherical shell. So if we think about another example, is if I took the surface of the Earth, if we regard the Earth as a perfect sphere, we take the surface of the Earth, that's a fixed radius away from the center, then how is my wave function changing along the surface of the Earth? Okay, so the next thing is just to give an example of a wave function, the 1s orbital wave function, and this is the ground state of hydrogen. Remember, like our electron from our hydrogen atom is in the 1s orbital. Our psi looks like this. So it looks like this function that I've written out, where we have this radial wave function portion to the left, and that's multiplied by an angular wave function portion. And there's some things to note in this function. First of all, a naught is our Bohr radius, right? And if we remember from when we calculated Rydberg's constant, the Bohr radius is the same radius we calculated during the derivation of Rydberg's constant, and we plug in n equals 1, which tells us it's the 1s orbital, and we plug in z equals 1, which tells us we're dealing with the hydrogen atom. So that we talked about in the Rydberg's constant video, and a naught is basically the n equals 1 shell radius that we calculated. So the two other things I want to note is let's look specifically at the r of r and the angular wave function, right? So our y of theta and phi, note that it's a constant number. It's 1 over 2 pi to the half, which is some constant, right? Basically, it doesn't depend on theta and phi. So what does this mean, right? If our angular wave function is constant, that basically means that our wave function, our orbital, is spherically symmetric, right? It doesn't have any angular dependence. So this sort of confirms our AP chemistry knowledge when we learned that 1s orbitals and s orbitals in general are spherically symmetric, right? The next thing I want to look at is the r of r, and we see that our r of r looks like some constant where we have 2 over a naught to the 3/2, but more importantly we have e to the negative r over a naught. So basically we have a constant times an exponential decay function, right? So r of r for our 1s orbital is an exponential decay. And this makes sense, right? Because farther away from the nucleus, there should be less probability we find the electron, right? Because this is in a 1s orbital, there's a higher probability you find the electron close to the nucleus than far away from the nucleus. And that's represented with our r of r, because remember that probability density is given by psi squared. So if we square this function, there's a dependence on r squared, right? So r is also telling us something about the probability density. And if with an exponential decay function, that means that r squared is also going to be an exponential decay function, which means that as I go farther away from the nucleus, the probability density will be lower, which makes sense. That's intuitive, right? So the last bullet point is just rehashing what I said before, that in a particle in a box, it's a one-dimensional wave function, so we only needed one quantum number. But with atomic orbitals, we need 3 quantum numbers because we have 3 dimensions. Okay, so this is just a representation, a graphical representation of spherical coordinates. So you can see that we have our r, which is our radius away from the center, right? We have our r, and we also have our theta and phi. And theta is latitude, right? We can sort of see that. That makes it, if we think of this as the Earth, right? Our theta is sort of telling us what is the latitude, and our phi is telling us what is the longitude, right? So hopefully this sort of clears up what I was saying in the previous slide by giving an image to go with it. So now I just want to discuss quantum numbers, and what exactly are quantum numbers and why are they important? So a quantum number basically specifies an orbital. So basically each orbital will have a unique set of quantum numbers. No 2 orbitals are going to have the same exact set of 3 quantum numbers. So it's basically like a key, right? If I know the set of quantum numbers, I know the orbital it's specifying. If I know the orbital, I should know the set of 3 quantum numbers, right? So now let's talk about what are the 3 quantum numbers and what do they represent, right? So the first quantum number is n. N is called the principal quantum number, and it tells us the size and the energy of the orbital. So have we seen n before? We have seen n before. Remember that when we were deriving Rydberg's constants and the energy levels in single electron atoms, n was the quantum number that gave us the allowed radii. This was when we were using the Bohr model of the atom, and we were trying to find which radii the electron could be at. So it told us the allowed radii, right? And this is basically analogous to the size. Also, we saw that when we were looking at for single electron atoms and ions, only n mattered for determining the energy. So we saw this also in the Rydberg's constant video when the energy of orbitals, the energy of the n equals 1 and n equals 2, right, they were degenerate in a single electron atom or ion. But note, right, only n matters for energy when we're looking at single electron systems. But when we look at multiple electron systems, take for example a carbon atom, right, the same orbitals with the same n might not have the same energy, right? So, and this is because we have shielding effects of other electrons that change the energies of the orbitals. So let's take carbon, and we see that carbon has 2s and 2p electrons. But the 2p electrons are higher in energy than the 2s electrons. And this is because the 2s electrons are more penetrating. And this is a vocab term we'll cover in another video. But all I wanted to do was show that quantum numbers with the same n and different other quantum numbers, right? The same n, they both have n equals 2. But they can have different energies because of shielding effects. The next quantum number I want to discuss is the L quantum number, right? So L is the orbital angular momentum quantum number. So this tells us the angular momentum, okay? So that's sort of an important thing. L describes the shape of the orbital. So L is basically telling us, is it an s orbital, a p orbital, a d orbital, f orbital, and on and on and on, right? So our n tells us, right, our n equals 2, for example. If we look at our n equals 2 shell, we have 2s and 2p orbitals. The s and p is specified by the L quantum number. Say for 3, we have n equals 3, we have 3s, 3p, 3d. The s, p, and the d are specified by the L quantum number. That's just examples. So L can take values from 0 to n minus 1. So L equals 0 implies S, L equals 1 implies P. So this is sort of like analogous terms, right? L equals 0 is the same as S orbital, L equals 1 is the same as a P orbital, L equals 2 is the same as a D orbital, L equals 3 is the same as an F orbital. So think about when we're looking at this, that it can only go to n minus 1, we can sort of think about this logically, right? If we take n equals 1, so our n equals 1 shell, we only have a 1s orbital. We don't have a 1p orbital, right? So that makes sense because L can only equal 0. L can only go up to n minus 1, which is 1 minus 1, which is 0, right? So we can only have a 1s orbital. For n equals 2, right, we have our 2s and 2p orbitals. So L can only go up to 2 minus 1, which is 1. So we have L equals 0 and L equals 1. This agrees with our sort of knowledge, right? And we can go on with n equals 3, right? With n equals 3, we have 3s, 3p, 3d, and this corresponds to L equals 0, 1, and 2. So hopefully that makes sense. Orbital angular momentum. So what does L tell us, right? L is supposed to tell us about the angular momentum. We can actually calculate the angular momentum, the orbital angular momentum, using the L quantum number. So orbital angular momentum basically means how fast does an electron in this orbital circle around the nucleus, right? So L, this is our orbital angular momentum, is equal to our L quantum number times L plus 1, and take the square root of that, and multiply that by the reduced Planck's constant. This is not really important to memorize, but it's really good for intuition. So one thing I want to talk about is the difference between the s orbital and the other orbitals when we look at the angular momentum. So note, right, for s, we have L equals 0, right? When we're looking at an s orbital, this has L equals 0. And what does L equals 0 mean? If we plug 0 into the angular momentum equation, we get that the angular momentum is 0. But for P, D, and F and on, right, for all other orbitals, we have that L is not equal to 0, right? So we have a non-zero angular momentum for all other orbitals. So let's talk about how that affects, what we see with wave functions, right? So an electron in the s orbital is distributed evenly around the nucleus. It isn't circulating around the nucleus, right? It has no angular momentum. And this is why only s electrons have non-zero probability density, so psi squared of 0 is not 0. So only s electrons have a non-zero probability density at the nucleus, right? So the wave function at 0, is non-zero at the nucleus, right? But since p, d, and f orbitals have a non-zero angular momentum, the closer they get to the nucleus, the more their velocity must increase, right? If we have angular momentum, that depends on both the radius and the velocity it's spinning around. So as the radius decreases, as we get closer to the nucleus, the more the velocity has to increase to keep the same angular momentum. And what happens when the velocity increases? The electron will be flung away from the nucleus, right? So as the electron gets closer, the velocity of the electron, it's spinning faster and faster. So it's basically going to get flung away from the nucleus, and it's not going to be able to approach the nucleus as much. So this is a really important point. This is why the psi squared of 0 is not equal to 0 for s orbitals, but it is equal to 0 for all the other orbitals. The next quantum number I want to talk about is the magnetic quantum number m sub L. This defines the orientation of the orbital motion of the electron. So for an example, right, we talked about how we have two p orbitals, right? Two p orbitals, but there's three 2p orbitals. There's the 2px, the 2py, the 2pz, right? And they all have different orientations in space. One is on the x-axis, one is on the y-axis, one is on the z-axis, right? So the magnetic quantum number is differentiating between these three. The magnetic quantum number can take the values from negative L to L. So this should make sense, right? If L equals 0, we're looking at an s orbital, sorry. So, and there's only one s orbital, right? So our m sub L can only equal 0, right? Because there's only one s orbital. But if we take L equals 1, right, our m sub L can equal -1, 0, or 1, which corresponds to the three p orbitals. And we can continue this, but I think you get the idea. What does the magnetic quantum number actually tell us? What can we calculate with it, right? Basically, it tells us how much of the total angular momentum found in our orbital angular momentum equation, right? When we talked about that with the L quantum number, it tells us how much of that angular momentum is around the axis given by the quantum number m sub L. And we can calculate that using this expression. Our angular momentum around that specific axis is equal to our m sub L times h bar. So now I want to talk about radial distribution functions and what exactly they mean, right? So what is a radial distribution function? The radial distribution function is the probability that an electron will be found anywhere in a shell of radius r. So what are we doing with the radial distribution function? We're taking out the ideas of the angular parts, right? We're sort of saying, okay, let me ignore the angle. I want, just if I take a shell at radius r, I want to know the probability that I find the electron there. That's what my radial distribution function is doing, right? We can calculate my radial distribution function by looking at this equation. P of r, which is my radial distribution function, equals r squared times our radial wave function squared of r. Why does this make sense, right? P of r should make intuitive sense. P of r should grow by r squared, grows by r squared. Why? Why should it grow by r squared? Because the surface area of my shell as I go outwards is increasing by r squared, right? So I have more sort of possible places to see my electron as I go farther and farther out. So my probability should increase by r squared. My surface area is increasing by r squared, so my probability should increase by r squared. Higher value of my radial wave function squared, right, r squared of r, should also make P of r grow. Why? Because that implies just a higher probability at that radius. So that should make sort of intuitive sense. For s orbitals only, if we do the math, right, if we try and solve for p of r, we can also represent p of r as 4 pi r squared times the wave function squared of r. Why does this sort of make sense, right? With s orbitals, our wave function is spherically symmetric. So if I take my psi squared r at a specific radius, if I look at a specific radius, right, and take my psi squared r, and then I sum that probability density over the entire surface area of the shell, right? My surface area of the shell is 4 pi r squared. So if I sum that probability density, if I take that constant probability density at that r and sum it up over the entire surface area of the shell, I should get my p of r, right? Okay, so what is the difference between p of r and psi squared r, right? What exactly is the difference? And this is a really important distinction, right? P of r versus psi squared r theta phi. What is the difference? P of r is summing up my psi squared over all the values of theta and phi at a given radius. So we're not worrying about theta and phi. We're sort of ignoring them and saying, okay, at this radius, sum up all the angles and tell me what is the probability I find it at this radius. Whereas psi squared is telling me at this angle it might be different than at that angle, right? But P of r is just looking at the radius. So that's an important distinction to make, and hopefully that cleared it up a little bit. Another thing to note is that P of 0 equals 0 for all orbitals. This means even s orbitals. So remember, s orbitals we had psi squared of 0 not equaling 0. But P of 0 for an s orbital equals 0. Why, right? Why is that? Why does that make sense? Even if psi squared is non-zero at a radius of 0 at the nucleus, the surface area of possible locations with r equals 0, right? The surface area of the possible locations is 0. There's really no place you can find the electron as you shrink the radius smaller and smaller. And so the probability you find an electron there is 0. So even though psi squared of 0 might not be 0, the actual probability you find the electron there is 0 because you've shrunken your radius to 0. So there's no surface area to actually observe the electron. So that can be a little confusing, but hopefully that again made a little bit of sense. And another thing to note is that the maximum of P of r for the 1s orbital is a0, which is the Bohr radius, which is the n equals 1 radius that we solved for in the Rydberg's constant video, right? So it should make sense that the maximum probability you find the electron in, the maximum probability radius you find the electron in, is the same one that we calculated previously using Bohr's model of the atom, right? So it sort of lines up a little bit with each other. Now I just want to look at some graphs of the radial distribution function, right? So what exactly do we want to, these are just sort of to observe what they look like, right? And make some sense out of them. So one thing to note, right? If we look at the 1s radial distribution function, you can see it peaks right here. And this peak corresponds to a0, our Bohr radius, right? Another thing to notice is that as n increases, so as we go from 1s to 2s to 3s, or 2p to 3p, right? As our n increases, what is happening to our peaks of our probability, of our radial distribution function, right? We can see that our peak shifts to the right. So with our 1s, we have our peak at a0. With our 2s, we have our peak farther to the right. 3s, we have our peak even farther. Same with 2p and 3p. As our n increases, our peak of our radial distribution function shifts to the right. What does that mean? Higher n values mean that the electron will be on average farther from the nucleus, right? They're going to be at a higher energy state on average when we have higher n values, and that means that the electrons are farther from the nucleus, they're less stable, right? So this is just one observation I wanted to make with the radial distribution function graphs. Now we're going to look at radial wave function graphs. And here I want to specifically talk about nodes, and more specifically radial nodes. So first we see our 1s radial wave function. And we can see in this we have like an exponential sort of decay, and that's what we talked about in one of our beginning slides, where we said that with 1s orbital we just have a radial exponential decay as our radial wave function. With 2s we can see we don't just have an exponential decay, we have a dip, and then it crosses 0. Our radial wave function crosses 0, and then we sort of settle in and then it approaches 0 as we increase the radius even farther. With 3s we have 2 nodes now. It crosses 0 twice, right? So an important thing to see is that with 2s we have 1 node, right? With 3s we have 2 nodes. And with 2p, you can see with 2p we never cross 0, right? We start at 0, our wave function starts at 0, but we never cross 0, right? Not like with our 2s where we cross 0. So we have 0 nodes for our 2p. So how can we calculate the number of radial nodes? We calculate the number of radial nodes using this equation. We take the n quantum number, subtract off the L quantum number, and minus 1 from that. So let's see if we can see how that works with the examples I've given. So let's say 2s, right? With 2s our n equals 2, our L equals 0. So the number of radial nodes should be n minus L minus 1, which is 2 minus 0 minus 1, which is 1, right? And we have 1 node. Now let's try it for 2p, right? The number of radial nodes for 2p is n minus L minus 1, which is 2 minus 1, because with a p we have n equals 2, L equals 1. So 2 minus 1 minus 1 equals 0. So we have 0 radial nodes, which is what we see on the graph. So here's just a way to sort of interpret the number of radial nodes using a graph and showing how that can be derived from this equation here. Now let's talk about boundary surfaces, and these are sort of the pictures you might have seen when you're looking at AP Chem, right? They're graphic representations of the atomic orbitals. So we can see that P of x, or the P orbitals, look like dumbbells, which you might have heard in AP Chem class. And there's one nodal surface. So what is the nodal surface? This is a nodal plane, right? Right through the center of the orbital, there's a place with 0 probability density, and that's called our nodal surface. So there's nodal surfaces on all 3 of them. It's right in the middle of this dumbbell sort of shape. Nodal surfaces are the same as angular nodes. So that's just something that's an equivalency to make in your mind, that you might hear the term nodal surface or you might hear the term angular nodes, but they're the same thing. If we look at the d orbitals, right, you might not have seen these pictures before, but they're very important when we're going to need to know the shapes of d orbitals later on. So it's sort of important to have these in your mind, even if you might not have gone into them in an AP Chemistry class. But these are the shapes of your d orbitals, and you can see that for all of the d orbitals you have 2 nodal surfaces, and they're shown graphically on this image. You can see there's 2 nodal surfaces for all of these d orbitals. So how do we calculate the number of angular nodes? The number of angular nodes is just given by L, our L quantum number. So with our p orbitals, right, p orbitals we have L equals 1, d orbitals we have L equals 2. So we have 2 nodal surfaces with d orbitals and 1 nodal surface with p orbitals. So now I want to discuss the final quantum number, which is the spin quantum number. So we talked about how when we have an orbital, say we have a 1s orbital, this is sort of described by an n quantum number, an L quantum number, and a magnetic m sub L quantum number, right? But say we have electrons in this orbital, right? If we fill this orbital up with electrons, we have one pointing up and one pointing down, right? We said that these 3 quantum numbers sort of act like a key for this orbital. No other orbital is going to have this exact set of quantum numbers. But how can we describe an electron, right? In the same way, no 2 electrons should have the same set of quantum numbers. So we can describe an electron by the three quantum numbers that describes its orbital. But each orbital holds 2 electrons, so we've narrowed it down to 2 electrons. But now we got to distinguish these 2 electrons from each other. That's where the spin quantum number comes in. So the spin quantum number distinguishes these 2 electrons, right? That's basically what it's distinguishing. And you can see that when I drew this, right, I drew one electron pointing up and the other pointing down. The one on the left is pointing up, and we call this spin up. The one on the right is pointing down, so we have this spin down. So what exactly is spin? Like, what does that mean, right? An electron in an orbital has 2 spin states. They're either up or down. That's what I just said with the 1s orbitals. Basically, we can think of an electron like a planet rotating on its axis. So we can see in this image, right, we can either have the electron spinning one way clockwise or spinning counterclockwise. These are the 2 spin states. So we can think of an electron like a planet on it rotating. And these 2 spin states are given by m sub s. And our m sub s can either equal plus half or minus half. So these two quantum numbers, these 2 values for the m sub s quantum number, refers to whether it's spinning clockwise or counterclockwise. And we can see that in this image, right? When we have spin up, it's rotating clockwise, and when we have spin down, it's rotating counterclockwise. So basically, this quantum number tells us which way the electron is, quote unquote, rotating, which way it's spinning. So how did we actually find out, right? How did we actually find out that there was only 2 spin states? This was found from the Stern-Gerlach experiment, which I just wrote is called the electron spin experiment. So this experiment showed that there was 2 spin states. How did it show this, right? Basically, they shot silver atoms through a magnet. Why did we shoot silver atoms through a magnet, right? Silver has 1 unpaired electron. It has 1 unpaired electron. So basically, all the other electrons in silver, all the other paired electrons in silver are kind of inert. They're paired, they're happy. But this 1 unpaired electron basically acts like an electron. So it basically, silver, in this case, acts like just an electron because all the other paired electrons don't really do anything. That's why they use silver, so we can sort of simulate the experience of it just being an electron. So what happened, right? What happened when we shot these silver atoms through the magnet? Basically, when we have an electron, the spin is either up or down. And what does that make the electron do? That makes the electron behave like a bar magnet, right? When we have a spinning sort of charge, right, this makes it behave like a bar magnet with a north pole. And depending on the spin, the north pole can either be pointing up or down, right? There's only 2 orientations for the electron magnetic field. Because if it's spinning counterclockwise, the north pole points one way. If it's spinning clockwise, the north pole points a different way. So we have 2 orientations. So what does this cause the silver atom to do, right? Because there's an external magnetic field, the magnetic field that's created from the spinning electron is going to interact with the external magnetic field. So the silver atoms either curve up or down depending on the way the north pole was oriented, right? If it's spinning clockwise, the north pole is going to be oriented differently from when it's spinning counterclockwise. And because of these different orientations of the north pole, the magnet is going to interact with the silver atoms differently depending on the spin state of the electron. And this is going to cause the silver atoms to either go up, or curve down based on the force that the external magnet exerts, right? So basically the silver atoms either curved up or down, and we only saw 2 different curvatures of the silver atoms. What does this mean? That means that there was 2 spin states. There weren't a bunch of different spin states, or there weren't only 1 spin state. If there were a bunch of different spin states, we would see many different curvatures. If there was 1 spin state, we would only see 1 curvature. But there was 2 spin states, right? We saw 2 curvatures, which showed that there are 2 spin states of the electron. Okay, so this was all I wanted to cover today. Hopefully this lecture made sense. Hopefully you learned something. Thank you so much for watching, and I'll see you guys in the next one.